All right, last class, we kind of just marathoned through talking about a bunch of intermolecular forces, and we left off, the last things that I was ranting and raving about was how you can dry your hands more efficiently with those air dryers in the bathrooms. And we talked about dynamic equilibrium just a little bit. We didn't look at what dynamic equilibrium is, but we talked about vapor pressure. Vapor pressure is the partial pressure of a gas at dynamic equilibrium. I think it says that on the previous slide, yeah. Vapor pressure is the partial pressure of the vapor in dynamic equilibrium with its liquid. And the reason that that dynamic equilibrium part is important is because the rates of evaporation and condensation are the same, and so we cut out surface area. Surface area increases vaporization, but it also increases condensation. And so since it's affected equally, we cut out the things that change our vapor pressure. So vapor pressure just increases with increasing temperature. The hotter that you get, like a bottle of water, if it's like half full, on a really hot day, you'll see a lot of condensation on the sides. On a really cold day, you won't see very much condensation on the sides. That's sort of like a visual that we've probably seen before of kind of how temperature might increase vapor pressure. Decreasing strength of intermolecular forces also affects vapor pressure. It's like you can't smell water very well. Not that you can really smell water anyway, but things that are really volatile, like acetone and just stuff that evaporates quickly, you can smell really well because it more easily goes into the gas phase. So here we've got a play-by-play of what establishing dynamic equilibrium might look like. So in frame one, we've got water in a sealed container, like a water bottle. So all of our water is down here in the bottom. And we don't have all of the individuals drawn out. And then some of the water molecules start to evaporate. That's that my favorite graph that I showed you last class, kind of towards the end, where you've got the distribution of energy of all of the different molecules, and some of them have enough energy that they can escape. So some of them have some energy to escape, and they do so, and they get into the gas phase. And then in step two, we've got some water vapor that starts to condense on the walls. So things that are running into the walls, they might hit it and lose some of their energy. It's not a perfectly elastic collision, so they don't bounce off like a bouncy ball. They might hit it, lose a little bit of their energy to the wall, and condense out. That's what you would see condensation. So like in your car in the winter, the condensation on your windshield, that's the sort of thing that's happening there. Some of it also crashes back into the water surface, and it returns to the liquid phase. Over time, these two rates, the rates that the water gets into the air and the rate that the water comes out of the air, will stabilize. And so this number of particles, if we extended out more frames, it would always be that number of particles if we're at dynamic equilibrium. It's set. We've got stuff that's going into the gas phase. We've got stuff that's coming out of the gas phase. Do we have any questions about that? Okay. One of the other phase changes, so we've talked about evaporation and condensation. Boiling is a process of evaporating, but it's a specific type. So the boiling point is the temperature at which the vapor pressure of the liquid is equal to the pressure above it. So its willingness to go into the air increases, its vapor pressure increases as temperature increases. So we've got a slow increase of our vapor pressure, and at some point our vapor pressure hits the atmospheric pressure, the pressure around the thing. When it hits that point, it's boiling. So equal to the pressure above it. Around here, it's about 1 atmosphere. If you go up further into the mountains, or go up into the mountains, it's going to be a lower vapor pressure, or lower atmospheric pressure. And so you don't have to heat a liquid up quite as much before it will start boiling. And what's special about a boiling point is that the thermal energy that the liquid has, in this case we're thinking about water, the thermal energy of the water has enough energy that you can form gas inside of the water. So rather than just with evaporation where we're losing it from the surface, when we're boiling, we've actually got water vapor forming inside of the body of water. It's got so much energy that it's creating a little gas pocket, and those gas pockets are less dense than the water, and so they float out. Since the pressure is lower at higher elevation, the boiling point is lower at higher elevation. Does anyone know what a pressure cooker is? An Instant Pot? Pressure cookers cook things really fast. You may know that. You can cook beans way faster than normal. You can cook rice way faster than normal. It takes a little bit of time to ramp up, but the cook time is like a couple minutes or 45 minutes, depending on what you're cooking. But it's way faster than if you just put it on the stove. And the reason for that is that a pressure cooker holds the pressure. So as you're heating up your liquid, it's building pressure inside, and it doesn't let that pressure get to a point where it can boil. So you're constantly increasing the pressure in the pressure cooker, and that means that the pressure can continue to rise. So this is a practical application, how pressure cookers work. Kind of like in a nutshell, they're the basic principle. Which allows the boiling point to rise. So your pressure in a pressure cooker increases. You're trapping all that pressure in there. That's why they can be dangerous if they're like in bad shape or if you heat them too much. And that allows the boiling point of the liquid to rise. Another thing that happens at boiling, so I kind of jumped the gun a little bit, when you reach the boiling point of a liquid, just like with the freezing or melting point, when you're at the boiling point, any additional heating only causes more rapid boiling. The temperature does not rise. So I usually say temperature is locked in at the boiling point. So if you're heating up a pot of water on the stove, or like when we were making metal soup last week with our calorimetry experiment, right, we're heating up our water, and I told you, you can heat it at 350 Celsius, 400 Celsius on the hot plate, and then once it starts to boil, turn it down. You're not going to get it any hotter than 100 degrees Celsius, probably a little lower because we're slightly higher elevation than sea level. It'll just boil more rapidly, and so you'll run out of water more quickly. As long as you've got a little bit of a boil, it should be right around boiling point. It's a little bit of plus or minus there. But just like when we were at the phase change of ice water is locked at 0 degrees Celsius. You may remember from last class. Same thing with boiling. The only time that the temperature will continue to rise past the boiling point is if you either increase the pressure, that lets the boiling point rise because the vapor pressure has to rise to match the outside temperature or outside pressure, or all of your liquid water has boiled and turned into the gas. So only after all the water has been converted to steam can the temperature of the steam rise beyond 100 degrees Celsius, and you wouldn't have any liquid water at that point. This also does another thing that's particularly magical. How many of you had made pasta before? Boiled water on the stove, throw some pasta in, you set a timer. Have you ever checked the temperature of the water when you were boiling your pasta? If you put brownies in the oven to make brownies, can you just set the oven to whatever temperature you want? Not really. You can't just say, well, I'm going to throw it in there, we'll max it out, we'll set it for 12 minutes. You'll come back and your brownies will be cooked. They'll be crispy. You'll be carbon brownies. They'll be burnt. The reason that you don't have to check the temperature and you just set a timer is because if your water is boiling with your pasta, you're locked in at the boiling point. So you're always going to have a nice consistent cook time for your pasta, assuming it's the same pasta and all these other things. But this is why you only set a time when you're making pasta. You don't have to check the temperature of the water because the people that wrote the instructions on the box know that the water is boiling, and so it's this temperature, and they've checked it. Some boxes of pasta or some meals, if they've got mountain folk in mind, might have instructions for at higher elevations. So it might say if you're at 7,000 feet or 10,000 feet, add 2 minutes, or double the cook time, or double the whatever every however many thousands of feet. Because the people that are writing those instructions know that at higher elevations, the boiling point is lower, and so it needs a little bit longer to cook for that food to be okay. All right, so lots of cool stuff. Now let's talk about energy. We've talked about this a little bit before with Q and exothermic and endothermic, so let's talk a little bit more or just remind ourselves. If you add ice to a drink, that ice cools the drink down because the ice is melting. The melting ice absorbs energy. Ice is the solid state. If we make a little one-axis graph, our lowest energy state is the solid. If you add more energy, it would become a liquid. If you add more energy, it becomes a gas. This is true for most things. So solid ice has to gain energy to become a liquid. So when your ice is melting, it's going from a solid to a liquid. This is how anything melts. When your ice is melting, it absorbs energy to turn into water, and that absorbs the heat that it needs to absorb, comes from the liquid that it's in. So that's why it cools your drink down. And the reason that it's endothermic is if we think about what's happening with our molecules or our atoms, in a solid, they're locked in place. They can't move past their neighbor, right? They're just vibrating in place. You need to give them a little bit more energy for them to be able to move past some of their neighbors. That's when they turn into a liquid. So they can move past each other. They're not completely locked in place, but they're still touchingly close because they're a liquid. The opposite state, opposite phase change of freezing, is going from a liquid to a solid. And our liquid has a little bit more freedom. We can move past our neighbors. They've got a bunch of energy, right? And in order for them to get locked in place, to not be able to move past their neighbors, we have to say, slow down, bucko, cool it. Take a little bit of energy out. If we cool down our liquid, if we release energy, if we steal energy, if liquid releases energy, then it will cool down and freeze into a solid, no longer having energy to escape moving past its neighbors. So the way that the magic of your freezer works, part of the magic of your freezer, I don't know if you know how magical freezers are. Freezers and refrigerators are like, it's crazy stuff they're doing there. It's not actually that crazy, but it is really cool. So as water in your freezer turns into ice, your freezer is just a very cold environment. The reason that it's magical is we're moving heat from inside of your freezer to outside of your freezer, and that's just crazy. So you're creating a cold environment, and the water that's in your freezer is releasing heat. It's getting sapped. The heat is leaving from the water and going into the cold environment, and then the compressor and whatnot pulls that heat out of the freezer. And so that energy needs to be released or removed by your refrigeration system, which is very cool. There's a quantity called heat of fusion. We can think of delta H as being heat. I think it's actually, if I'm remembering correctly, my brain's a little fried. I think it's enthalpy, but we'll just call it heat. And FUS standing for fusion. Fusion referring to melting or freezing, depending on whether you're looking at the positive or negative. I think I've looked up why is it fusion, because that doesn't make sense, and I don't remember what I found. Answers are out there on the internet if you look for them, usually. So the heat of fusion for water, the amount of energy that water takes to melt, is 6.02 kilojoules per mole. If you remember from our calorimetry experiment, some of you had an amount of heat that was transferred from your boiling hot metal to 50 grams of water that was like 1,500, 2,000 joules. So that's like a third of what we would need to melt or freeze 1 mole of water, which is 18 grams, and we were using 50 grams of water. So it's a lot of energy. So the way that we might describe this in an equation, H2O going from the solid form to the liquid form, so melting, has this delta H value. We're not saying that it's fusion, it's just a delta H of plus 6.02 kilojoules. This plus is often omitted, so if there's no plus, pretend that it's positive. That's what we usually do anyway, so that's not new. And then the positive, not being negative, means that energy is going in. So this energy is being added. It's going into what we would describe as the system, the thing that we care about, the thing that's our focus. So this delta H is positive. Melting is endothermic. We have to go up our chain of energy states. We're going from a solid to a liquid. We need to add in a little bit of energy for our molecules to be able to move past each other. There's also an implied per mole. You'll almost never see that if we're showing a delta H off to the side of an equation like this. You just have to know that it's per mole. So you need to know it is per mole, because that will almost never be given to you. Unless it's like a header in a table and it tells you what the units are, then it might say kilojoules per mole. If we go the other direction, so if we do liquid to solid, now the sign is negative. It's the same amount of energy. So we just changed the direction. We flipped our thing left and right. And now instead of having to put in energy to get it to heat up, to get it to melt, to go from a solid to a liquid, now we're going the other direction. So we're going from a liquid to a solid. And so we have to lose the same amount of energy. Same amount of energy as melting. It's just opposite. Again, there's that assumed per mole that's in there. So if we were freezing 36 grams of water, how much heat is lost? Just to give us an example, working with some simple numbers to do a calculation. So the starting amount, 36 grams, we know that it's H2O water. So 36 grams of H2O, our molar mass of water is right around 18. I'm just going to call it 18. That's why I picked 36, so it would work out nicely. All right, so we can see 36 over 18, that's 2, trust me. So 2 moles of water. And we can multiply by this 6.02 kilojoules per mole. So for melting or freezing, 1 mole of water, it's 6.02 kilojoules. It's either releasing or it's absorbing, depending on which direction we're going, freezing, melting, melting, freezing. And so the number that you would get out if you did this calculation would be 12.04, somewhere in that vicinity, kilojoules. And now I'm going to show you another reason why these types of questions can be tricky. That is not the correct answer. Because the question that was asked is how much heat is lost. And so we're asking how much negative heat. And so the correct answer would be 12.04 kilojoules. Was or is lost. It's not always going to be like a tricky wording like that, but there is often language in these types of questions about whether the heat is being lost or absorbed. And so there can be some negatives that we have to do in there, which on top of not having the per mole part shown in there can be confusing. Questions? All right, so 6.02 kilojoules for heat of fusion. This is basically just what we did in that little practice problem. So we can use the heat of fusion to calculate the amount of heat required to melt a given amount of solid or freeze. We can use the heat of fusion as a conversion factor between moles of the solid or of the liquid and the amount of heat because of that secret per mole part. So since we have kilojoules and moles, that lets us convert between the two things. So it could also ask you, hey, I've got this amount of heat. I've got 55 kilojoules of heat. How much water can you melt with that? Or how much ice can you melt with that amount of heat? Would be another sort of example question. All right, calculate the amount of heat absorbed when a 25.4 gram ice cube melts at 0 degrees Celsius. The heat of fusion for water at degrees Celsius, 0 degrees Celsius, is 6.02 kilojoules per mole. Usually you can just ignore the at 0 degrees Celsius. That's for the actually sort of folks. So give that a try. I'll give you like 2 minutes. All right. 25.4 gram ice cube. So we've got 25.4 grams of H2O. And we want to calculate the amount of heat absorbed. So we're looking for what's the positive number that we get out. Absorbed means we're adding heat. And we're given a delta H of 6.02 kilojoules per mole. Since it wasn't given to us in that like chemical equation format, we have the per mole part shown to us here. So in order for us to be able to use this kilojoules per mole, we need to get it into moles first. That's what the moles part of it tells us. We've got grams. We can convert to moles. We just divide by 18.015 grams per mole, which is our molar mass for water. 2 hydrogens, 1 oxygen. And then we would multiply by 6.02 kilojoules per mole, and the moles would cancel out. Optionally, you could have the H2O in there if you really want to cancel out your H2O. So 25.4 divided by 18.015 times 6.02, and remember that it's in kilojoules. So 8.49, after we round it for 3 significant figures, kilojoules. So this would be the amount of heat that's going into the ice cube, this little 25-gram ice cube, in order to get it to melt. Questions? All right. So that's one of our sets of phase changes. We also have evaporation and condensation, and it's a similar set of ideas. But if we think of what's happening in evaporation, I'm going to draw out my favorite one-axis graph. Solids are lowest energy, liquids are mediumest energy, and gas is our highest energy state. So evaporation is going from a liquid to a gas. So this is going to be endothermic. You have to put energy in. If you put water in a pot on your stove and you just wait for it to boil and you never turn the stove on, it's never going to boil. You got to crank the heat up and let it run for a while to get your water to boil. So we have to put energy in. That means that it's endothermic. And when we're converting from a liquid to a gas, our liquid is touchingly close. Our water molecules are right next to their neighbors. They can move past their neighbors. That's why liquid water runs. They're not completely locked in place. And then switching to a gas, they're completely separated from their neighbors. So we have a lot of attractive forces to overcome in order for us to boil our water. Our bodies take advantage of this endothermic nature of evaporation for cooling. So the fact that energy goes in to cause evaporation, that's why we sweat, and that's why a cool breeze feels so nice when you're sweaty on a hot day. Or if you're just warm, you can put water on your forearms. You got a lot of veins in your forearms, and that'll help evaporate some of the sweat too, or maybe a cold towel on your neck, whatever you want to do. All right, there's lots of ways that we can take advantage of the endothermic nature of evaporation to pull heat from our bodies and send it out away from us. So sweat evaporates, it cools down our bodies by absorbing our heat. A breeze intensifies that cooling effect because you're rapidly removing all of those little gas molecules. They don't have time to leave and then come back. So the breeze helps sweep those away. There's probably some pressure stuff going on in there too, but that's my theory. If you have high humidity, that means that you are relatively close to having the maximum number of water molecules that you can in the air. So there's a limit to how much water you can put in the air. It goes up as the temperature goes up. So if you've got really high humidity, the reason that it feels so suffocating is that you'll sweat and there's not much room for it to evaporate. And so you get greatly reduced evaporation from your skin, and so you don't cool down nearly as much. So we've got that phrase, but it's a dry heat. I don't know if you've heard yourself saying this or if you've heard others saying this to other people about, why do you live near Fresno? It's so hot there. You know, it's 115 degrees or it's 100 plus all summer. But it's a dry heat, right? But it's a dry heat means that our sweat actually evaporates. We can actually cool down. It's really not actually that bad if it's high 90s, low hundreds and you're sitting in the shade. It's really not that bad as long as you're sweating a little bit. Whereas 90 degrees in 90% humidity is suffocating. if you've never been out to somewhere that has high humidity in the summer, it's really awful, especially if they don't have air conditioning. So next time that if you go somewhere during the summer, or if you go down to the southern hemisphere during the winter here, and there's high humidity and relatively high temperature, even if it's only 90 degrees, pay attention to how awful it feels. Pay attention to how you step out of the shower and you felt really nice in the shower, and then suddenly you are just soaked in sweat again. And then you can think about, but it's a dry heat, because thank goodness it's a dry heat. Or if we get a little bit of sprinkle, a little bit of a rain here, and the humidity spikes, it's the worst. All right, condensation is exothermic. So I'm going to copy paste this. Wrong thing. Copy paste this, duplicate. All right, so if we're going from a gas to a liquid, we need to lose energy. We're going from being completely free molecules to being shackled to our neighbors, but still able to move around them. So you have to release heat for a gas to condense to a liquid. This is why steam burns are particularly bad, because steam is already over 100 degrees Celsius, over 212 degrees Fahrenheit. It can be much higher than that since it's a gas. It could be 300, 400, 500 degrees Fahrenheit. And then when it hits your skin, on top of being super hot, it's also dumping a ton of heat to condense onto your skin. And the amount of heat we'll see is really high. The exothermic nature of condensation is also one reason that overnight temperatures don't get as low when the humidity is higher. So you may know, or you may not have paid attention to this at all. Around here, this is just an FYI, temperature can, we'll write fluctuate. We can get swings of like 40 degrees Fahrenheit from our low temperature to our high temperature. Like you wake up in the morning and it's nice, it's a wonderful temperature. And then kind of more towards 4 or 5 in the afternoon, it starts to get baking hot. If you've looked at the temperature in places that have high humidity, so places like San Francisco, since it's a peninsula and it's surrounded by water, temperature changes more like 10 to 20 degrees over the course of the day. So you wake up, you go outside, it's a nice day. 4 or 5 in the afternoon, it's a nice day, but it's a little warmer. And a part of that is because of the high humidity. Because when it cools down at night, you've got a lot of water in the air. That water, if relative humidity drops below 100 or would drop below 100, then you've got water that's going to condense out. That's when you get dew or like condensation on your windshield or whatever. And when it condenses, it releases a bunch of heat out into the atmosphere. And so that kind of helps keep the surrounding air a little bit warmer. Now looking at numbers, heat of vaporization, so VAP here for vaporization. I don't want to write it out again, so I'll just link it. And then the delta H, again, we can think of as heat. This is the amount of heat required to vaporize 1 mole of liquid. So we're looking at going from the liquid to the gas. A lot of this is kind of the same as what we've seen before. And we're typically going to look at it at its normal boiling point. You can also find information for different temperatures. So like you can find a delta H VAP of water at 25 degrees Celsius. It'll still vaporize, just to a lesser extent. We usually look at it at 100 degrees Celsius, so you don't have to worry about that. This amount of heat is 40.7 kilojoules. Who remembers what our heat of fusion was, approximately? It was like 6. it was 6.02 kilojoules. So this is more than 6 times the amount of heat to go from a liquid to a gas compared to going from a solid to a liquid. It's a lot more heat, which is great because that means that we cool down a lot when we sweat. A fun thought experiment that I had a while ago is, what if these two numbers were swapped? How would that, obviously the world would break down, but like, just what would that experience be like? Because then you'd have to sweat like 7 times the amount to get the same amount of cooling, and that just sounds miserable. All right, so there's that. If we go in the other direction, now it's a negative sign. So going from a gas to a liquid, it's exothermic. Gas loses energy to become liquid. These delta H vap numbers, delta H fuse, all that, you don't need to memorize them, but you do need to know how to read and interpret the numbers if you're given them. Okay, so just like with fusion, with melting and freezing, we can use the heat of vaporization, that HVAP number, to calculate the amount of heat energy in kilojoules or joules required to vaporize a given amount of liquid. This is basically the same slide that we saw for the other set of conversions. So let's give that a try. Calculate the amount of heat in kilojoules required to vaporize 1.75 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. So we are looking for heat in kilojoules. We are given 1.75 kilograms of water. And we are also told the heat of vaporization. Again, we're given the per mole part. We won't necessarily have that on an exam. .75 kilograms of H2O we can convert to grams. There are 1,000 grams in 1 kilogram. Or those of you that have practiced it a lot, you would just move the decimal place over 3 spots. It's 750 grams. But we'll do the full unit conversion here. So now we've got it into grams, and the steps are very similar to the other example that we did. We need to convert to moles, and so we're going to divide by our molar mass. Molar mass has units of grams per mole, so we can use it to convert between grams and moles. Some units cancel out, and we've got some amount of moles that we would get out here. And then we need to use our delta H vap, 40.7 kilojoules per mole. Optionally add that H2O. That's what our calculation route would look like. Our solution map. Any questions about this setup? So we would get out 3,953.649736 kilojoules, and that turns into 3.95 times 10 to the 3 kilojoules. So that's the amount of heat that we would have to put in to about half a gallon of water. That's what 1.75 kilograms is. To get it to boil, or to get it to turn all the way from a liquid into a gas. Bonus, Now, knowing that this is a bonus slide, would you like to try it, or would you like me to just show you how to do it? It's a fun problem. Great. Love that we're being very consistent about our amount of input. We'll pause here. Forgot that I also need to give you the delta HVAP for water at 25 degrees Celsius. It's about 44 kilojoules per mole. So I gave some people in the class a little break, some time to work on the problem. We got a bit of a two-parter. And by a bit of a two-parter, I mean we have a two-parter. So a drop of water weighing 0.48 grams condenses here being a keyword, on the surface of the 55-gram block of aluminum, initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? And we are also given the specific heat capacity of aluminum at 0.903 joules per gram degree Celsius, which hopefully has you thinking Q equals MC delta T, because we'll also need that equation. So initially, the first thing we want to do is figure out how much heat is released during condensation. So heat from condensation, we've got 0.48 grams of H2O. We can convert that to moles of H2O. And then we can use this 44 kilojoules per mole to figure out the amount of heat released. So we've got an intermediate value that we're going to get here, 0.48 divided by 18.015 times 44. This is 1.172 ... meaning there's other stuff there, and I just don't want to write it. So this is the amount of heat that is released during condensation. If we were talking about this amount of heat, just generally without talking about this is the amount that's released, should this have a negative sign or a positive sign? Did the water gain or lose heat when it condensed? It lost. So this should have a negative sign in front of it. If a lot of these types of problems with heat change and stuff, you can just, if you understand how loss and gain work and what that means for positive, negative, you can just fix it. Like we know that it lost the heat, so it has to be a negative number. So this is the amount of heat lost by the water, 1.172 and some change kilojoules. That heat went entirely into the metal. So a positive 1.172 and change kilojoules gained by the aluminum. So this is our Q value that we're going to use in this Q equals MC delta T. We have now Q. We just figured out Q. We were given the mass, and we were given the C value. So what we're solving for in Q equals MC delta T is the delta T. Delta T equals Q over MC. So step 2, we're going to find the delta T. That way we can figure out what the final temperature is. So it's equal to Q 1.172 ... kilojoules. Probably should keep track of that being two significant figures. Kilojoules over grams, 55 grams, and C, which is 0.903 kilojoules per gram degrees Celsius. So the gram degrees Celsius could flip to the top. There's a problem. What's the problem? This is what I get to do when I look at your labs. Not that I necessarily know there's a problem. Get to look through them for problems. What's the problem in this case with this particular thing? What have we done wrong here? It's the right equation. Everything's in the spot that we said it was going to go into. The problem is that grams cancel. Degrees Celsius is what we expect to be left with. We've got kilojoules on the top and joules on the bottom. That's the problem. And so I'm going to sneakily convert that into joules. So now it's 1,172 joules. And now there's no problem. Problem solved. So 1,172 and change divided by 55, also divided by 0.903. Our delta T is 23.6 and change degrees Celsius with two significant figures. Is that our final temperature? No, it's not our final temperature. That's our delta T. Delta T equals TF minus TI. This is the amount of degrees that our temperature increased. Delta T plus TI equals TF. So 23.6 degrees Celsius plus 25 degrees Celsius and round for 1 decimal place, or sorry, 0 decimal places. This turns into 49 degrees Celsius. Which is quite a bit of heat to be gained by half a gram of water. I think 55 grams is about the size of those aluminum cylinders that we were using for the calorimetry lab. I think those were kind of in the ballpark of 55 grams. So if you can imagine like 1 drop of water condensing on the aluminum and it raising it to hot, like 120, 115 Fahrenheit maybe, somewhere in there, from room temperature. That's the sort of heat that we're talking about here. It's a lot. Questions? This is the sort of thing that I would expect maximum 1 question on an exam, because I think it's fun. And sometimes I choose violence. Okay, other things that we can do with heat, endothermic, and exothermic, and heating, we can look at graphs. We've got a graph here. We've got time in minutes on the x-axis. We are continually adding heat in. So you can think of this time as heat added or time on a stove. And on our y-axis, we've got the temperature of the water. So from A to B, we are heating ice. So for our A to B, this little line segment, we have ice. And then we get to 0 degrees Celsius. What's special about 0 degrees Celsius for water? Yeah, it's the melting / freezing point. And so our temperature locks in. We cannot increase our temperature. We cannot decrease our temperature because we have two states existing at the same time. So we have ice and liquid water at this B to C. So we've got an ice chunk, maybe we pulled out of the freezer, we set it into a pan on the stove, and at B to C, the ice is now melting. It's gotten up to the melting point, so it's turning into liquid water. Once it's completely turned into liquid water, then it starts to heat up again. That's what's happening at this C to D line segment. And then it gets up to 100 degrees Celsius, and the temperature locks out again. The reason the temperature locks out again is because we are at the boiling point. And so we have liquid and gas at this long D to E segment. The D to E segment is so much longer than our B to C segment because our delta H vap, or heat of vaporization, is like 6.5 times bigger than our delta H fusion, the amount of heat that we need to melt ice. And then the temperature can go up only once all of the liquid is gone. So the liquid is now gone at E, and it's just gas. And so the steam can heat up. We would have to have some sort of weird contraption to actually be able to do this. So let's just pretend we've got a magical pot on our stove that traps the steam. Questions about how we figured out what's going on at any of those line segments? Now, if you thought the last bonus problem was fun, there's even more fun that can be had. So this is basically describing that graph that we looked at. So we've got a 50-gram ice cube. It's at 0 degrees Celsius. We could start it below 0 degrees Celsius as well. We add it to 500 milliliters of tea at 20 degrees Celsius. So like 2 cups of tea, basically. We made ourselves a pot of tea at 20 degrees Celsius. Oh, this is actually maybe not the one that I'm thinking of. I switched my slides a bit ago, a year ago. What is the temperature of the tea when the ice cube has just finished melting? This is not as dastardly of a question. I'm going to skip it though. The way that you would solve this problem is this the right one? Okay, great. So the key phrase here, just finished melting, that's crucial to this not being an insane problem. If it doesn't say just finished melting, then this problem becomes a lot more difficult. So we're calculating how much heat is released by the 50 grams of ice, or how much heat is absorbed by the 50 grams of ice when it melts. So we're going to use our delta H fusion, turn 50 grams into moles, multiply it by this delta H fusion. That figures out how much heat is absorbed by the ice. And then we take our 500 milliliters of water, 1 gram per milliliter, so 500 grams of water, and we do a Q equals MC delta T. It's the same thing as the water drop problem, but for an ice cube melting. The way that it would get super difficult is if we want the actual final temperature of the mixture of the ice cube and the water, because then we have to figure out what's the temperature of the tea and what's the temperature of the ice water when it finishes melting, and how do those meet in the middle. And since they're both water, it's not quite as difficult as it could be, but it still would not be fun. Any questions about our phase changes and energy related to those? If you'd like to try the solution, have me look over it, I'd be happy to do that. But it's the same as the other problem, essentially. Okay, solutions are for homogeneous mixtures. So a solution is a homogeneous mixture of two or more substances, meaning that they're mixed together and it's the same consistency throughout. So think of Dr. Pepper, Mountain Dew Baja Blast, other such enjoyable beverages like those, things that aren't chunky, right? Homogeneous mixture, same consistency throughout. Solutions are all over the place. They are not just liquids. They can also be gases. They can also be solids. The ocean is an example of a solution. It's salt and other solids and liquids dissolved in water. Blood plasma, the stuff that runs through us, is a solution of several solids and some gases that are dissolved in water. So here's some types of solutions, and don't worry about what solvent, solute means yet. We haven't talked about that. I think it's the next slide. So basically you can think of solvent as being one component and solute being another component. So we can have a gas in a gas. So air would be an example of a solution of gases. We've got nitrogen, oxygen, we've got carbon dioxide, argon, a couple of other things in there. They're mixed evenly. We don't have like pockets of oxygen in the room and then other pockets that are just all the CO2 where you're like suffocating, right? The air is, for the most part, evenly mixed, and so you get a nice, consistent breathing experience throughout your life. So that would be an example of gas in gas, gas in liquid, like carbonated beverages. You can see the gas come out. You can shake it to get some of the gas out. Liquids can dissolve in liquids. Solids can dissolve in liquids like salt water. Gases can even dissolve in solids, and liquids can dissolve in solids, and solids can also dissolve in solids. So there's a lot of different types of solutions. So the whole point of this slide is just to let you know that there's lots of different types of solutions. We primarily think of one of these categories as solutions. One or two of these categories as solutions. A solution has at least two components. In order for it to be a mixture, you have to have at least two things. Otherwise, it's just a pure substance. So a solution has at least two components. Informally, our definition for a solvent is that it's the majority component. So there's more of this one. For air, air is mostly nitrogen, so nitrogen would be considered the solvent. So if we're thinking of air as a solution, nitrogen is our solvent. And then the solute is the minority component, or minority components, because you can have multiple. So oxygen would be a solute. So oxygen, O2, would be a solute, CO2 would be another solute, argon would be another solute, and whatever other trace gases might be present. Typically, though, we are talking about solid-liquid solutions. So we've got a solid and a liquid mixed together, and we usually consider the liquid to be the solvent, regardless of the proportions. So another way that you can read solvent is just as the liquid. What liquid are you using to dissolve the solids, to make the solids into a solution? The most common solutions, especially ones that we encounter, are those that have water as the solvent, as the liquid. It's also usually the majority component, but it's strictly speaking not always the majority component, just usually. So aqueous solutions, water, and something or some things else. Simple syrup, where you've got sugar and water mixed together. That's an aqueous solution. Milk is an aqueous solution. Dr. Pepper is an aqueous solution. Not everything is always aqueous solutions. There are other solvents, other liquids that are also used, especially if we have nonpolar solutes. Since water is polar, it's not going to dissolve nonpolar solutes very well, so we would want to use something that's a nonpolar solvent, like hexane. So remember that like dissolves like, so different solvents are needed in different situations. Polar solvents dissolve polar solutes, so like water dissolves sugar. Nonpolar solvents dissolve nonpolar solutes, like xylenes or chloroform can dissolve, I don't know, fat, presumably. Some examples of common polar solvents: water, acetone, methyl, ethyl, isopropyl alcohols. Some common nonpolar solvents: hexane, diethyl ether, toluene. The ones that you should know here is basically just that water is a polar solvent. The way that dissolution works or doesn't work, if you add a solid, if it's an ionic compound, into a liquid, there's competition between the solvent and the solute. So in this case, we're looking at table salt. So water has an attractive force with other water molecules. The sodium ion has an attractive force with the chloride ion. In order for us to break up the NaCl with our water, these interactions between the water and the sodium chloride have to be stronger. So the solvent-solute interaction needs to be stronger than the solvent or the solute-solute interaction. Otherwise, we won't separate the sodium and the chloride. For table salt, this is true. For NaCl, this is true. This is not true for all ionic compounds. So not everything that's got a metal and a nonmetal or a cation and an anion is going to be soluble in water. For example, calcium carbonate doesn't dissolve. So Ca2 plus and CO3 2 minus have a stronger solute force. Water can't dissolve it. Water can't break it apart. So it doesn't dissolve, it stays as a solid. The actual nuts and bolts of how it looks in solution is something like this. So we've got sodium chloride, we've got a bunch of repeating units of sodium and chloride. The positive ends of the water dipoles, so that's the hydrogen ends, are attracted to the negatively charged ions. In this case, that's chloride. The negatively charged ends of the water dipoles are attracted to the positively charged sodium ions. The reason for this is, opposites attract for magnets. This also stabilizes the ions so that they can actually exist. So when we dissolve stuff in water, we usually have just shown it as individual ions floating around. In actuality, they're surrounded by lots of little water molecules that are oriented in such a way that the charges interact nicely. So this is how ions actually look in solution. And for whatever reason, my brain always thinks of the part of the Toy Story movie where Buzz Lightyear is in the claw machine at Pizza Planet and there's the little green men all around him. Okay, so here's sodium chloride, more salt. The sodium and the chlorides we usually show just like this. The water molecules surround and pull apart and rip this sodium chloride to shreds. to individual ions in the solution. In reality, NaClAq does not contain any NaCl units. So nowhere in a dissolved solution of sodium chloride are you going to find an Na and a Cl stuck to each other. This is a substance that completely dissociates into ions, meaning there's none of the formula units intact. We call this a strong electrolyte. So strong meaning that it completely dissociates or completely breaks apart. And electrolytes, meaning that it's ions or conducts electricity. Not everything is a strong electrolyte, but this is, and I'm jumping the gun. This is our fourth force. You remember we had learned 3 forces before. Go ahead and think through what they are. So the 3 other forces that we learned are dispersion forces. Everything has dispersion forces. We learned about the dipole-dipole force. All polar molecules have the dipole-dipole force. And we also learned about hydrogen bonding and a subset of polar molecules, things that have hydrogen bonded directly to fluorine, oxygen, or nitrogen, can also engage in hydrogen bonding. And our 4th force is the ion-dipole force. So just like with the dipole-dipole force, the dipole-dipole force, the reason that it's hyphenated, is we've got a dipole interacting with another dipole. So it's describing the 2 things that are interacting. The ion-dipole force works the same way. We've got an ion interacting with a dipole. So ion, like Na+, and a dipole, an end of a polar molecule. It's those 2 things interacting. So we've got full positive or negative charge interacting with partial positive, partial negative charge. The ion-dipole force occurs when we've got mixtures of ionic compounds, since those provide the ions, and polar compounds, which provide the dipole. Typically in aqueous solutions of ionic compounds. And then we've got the close-up of that image that we saw before. We've got the positively charged sodium ion interacting with the negatively charged, the partial negative charged dipole of the oxygen in water. We've got the chloride negatively charged ion interacting with the positively charged hydrogen dipoles. You may not know this, but pure water, like just H2O, does not conduct electricity, or at least not very well. It's actually highly resistive to electricity, which maybe goes against what some of the things that you've heard about the dangers of electricity and water are. But that's because you have not experienced, you have never been around pure water, and I haven't either, and we probably never will. I've been around close to pure water. Puff my chest out a little bit about that. It's really not that special. But none of us have been around perfectly pure water. We probably never will be. We've maybe been around some stuff that was pretty close, though. So pure water doesn't actually conduct electricity. Ions, like in a sodium chloride solution, can conduct electricity. So ions conduct electricity, which is the reason that electricity in water is dangerous, because usually the water that we are coming in contact with has ions dissolved in it. If it's drinking water, it's either for taste or it's for dental health, or it just happens to be there and it's not worth getting rid of. In other cases, it's like distilled water or deionized water. There's probably still going to be some ions in there that still allow us to conduct electricity. And that's why water and electricity don't mix well. They're bad for you. So things like KCl, strong electrolyte solutions, the strong again meaning that they separate completely, and the electrolyte part just meaning that they're ions, they conduct electricity. In theory, if you were perfectly clean and weren't going to release any electrolytes into water, and you got perfectly pure water, and you took a bath, you could operate a toaster in the bathtub, assuming it wasn't like in the water, because it probably would be fine. You could safely make toast in the bathtub, and you wouldn't have to worry about getting electrocuted to death. However, in reality, that's not going to happen, and so it's best that you just make the toast beforehand and then bring it into the bath with you. Okay, so electrolyte solutions contain dissolved ions, as mentioned previously, and conduct electricity. Non-electrolyte solutions are not electrolyte solutions, so they don't conduct electricity. So they'll contain neutral molecules. Like sugar, for example. So if you get distilled water and mix some sugar into it, in theory it should be low conductivity at least, compared to salt water, which would be high conductivity. Silver nitrate, AgNO3, if you dissolve that into water, it might look something like this. AgNO3 is a strong electrolyte solution, and it doesn't contain, notice that there are no AgNO3 present in the solution. That's how we're representing that it's a strong electrolyte solution. And a key point here, when compounds containing polyatomic ions dissolve, the polyatomic ions stay as intact units. So our Ag plus pops off because it's a strong electrolyte solution, and our NO3 minus, our nitrate, stays intact as NO3 minus units. It doesn't break down into nitrogen and oxygen. We're just pulling apart the ions, we're not destroying the ions. So the ions are merely separated from each other. This would be like if we're breaking up a fight between two kids, that's kind of what water is doing. We're breaking up the fight between the two kids. We're not pulling them apart and then destroying them, because that would be illegal. However, AgCl does not dissolve in water. So this is an example of what that might look like. AgCl we've got represented here as this little crystal cube, and water all around it, frustratingly trying to pull it apart and not succeeding. So AgCl remains as solid AgCl when it's in liquid water, doesn't dissolve into independent ions. This brings us to solubility. This is a repeat of stuff that we've talked about before. Solubility, a compound is soluble, meaning that it will dissolve if it dissolves. So sodium chloride is soluble in water because it will dissolve, it will separate into its separate ions in water. A compound is insoluble or not soluble if it doesn't dissolve in the liquid. For ionic compounds, we've got some empirical rules, experimental rules, that can guide us on whether things dissolve or not. And this is the other side of the green sheet that we haven't used. So if you take out your green sheet and you look at the side that says solubility table on the top, that's our solubility table. Wow. There are many exceptions to solubility rules. Here's the one that you see on the book online. Combining two tables, table 9.4.3.1 and table 9.4.3.2. The general principle of how solubility tables work is the same, though, even if they look a little different. So we're going to look at the top part and show you how to read a solubility table. So top part, we're looking at things that are soluble in water. So we've got everything that's in group 1A, so our alkali metals, lithium, sodium, potassium, rubidium, cesium, and ammonium salts. So if you've got NH4 plus on the front of an ionic compound, then that will also be soluble. Anything that's a nitrate, NO3 minus, anything that's a chlorate, ClO3 minus, perchlorate, ClO4 minus, and acetates, C2H3O2 minus, those are also soluble. For sulfates, SO42 minus, there are some exceptions. So they're generally going to be soluble in water if there's sulfates. If there's an SO42 minus in there, it'll be soluble, except when it's paired with calcium, barium, strontium, or lead-2. So these are not soluble or insoluble. For our green sheet, it works about the same, but you're given the chemical formula instead of the name. So it's a little bit easier in some ways. So for example, on ours, for our third line, for our green sheet, Cl minus, Br minus, I minus, those are generally soluble, except if they're paired with silver, mercury, whatever that is, and lead-2 plus. So if we're paired with one of those, like AgCl, then it would be not soluble. So soluble if you see it on the left, unless there's an exception, then it's not soluble. And then we also have the sparingly soluble, which we can think of as not soluble table, which is usually below. It's the same on our green sheet. So carbonates and phosphates are not soluble. They're not soluble unless they're paired with things like sodium, potassium, ammonium. So BaCO3, not soluble. Na2CO3, soluble, because it's one of our exceptions. So we basically flipped what's what, where's where. Questions? You are not expected to have the solubility table memorized, although some instructors do that. So our solubility rules give us a qualitative description. Does it dissolve or not? Not the extent to which it dissolves, so no numbers. Dissolves or not. It's a quality, not a quantity. It's not a number. Gives us a qualitative description of whether these things are soluble. Molecular solids can also be soluble depending on whether the solid is polar. Generally, if it's polar, it will dissolve in water. If it's nonpolar, it won't dissolve in water. Like dissolves like. Okay, to see whether we can read these tables, please determine whether each of these compounds is soluble or insoluble. All right, that was a little bit of time to look at stuff, so we'll go through it. We've got, first up, calcium sulfide. So part of at least for this version of the solubility table, you do need to know the nomenclature. So this is calcium sulfide, which means that it's a sulfide. So calcium sulfide, we can find sulfides in our sparingly soluble, aka not soluble table. So all sulfides showing up down there. And let's check to see if we have some exceptions. So initially it looks like it's not soluble, group 1A, 2A, and NH4 plus salts, and also MgS, CaS, BaS sparingly soluble. So we would say that this is sparingly soluble or not soluble. On our green sheet, it says except those of group 1, NH4 plus, Ca2 plus, Sr2 plus, and Ba2 plus. So I guess it is probably a little bit soluble. One of the reasons that I don't like this version. Sparingly soluble. So it'll dissolve, but not very much. And then we've got FeSO4, iron 2 sulfate. I should do this in a different color. Iron 2 sulfate. We've got all sulfates in the soluble in water category. There's no exception for Fe2 plus. So we would expect that this is soluble. Then we've got lead 2 carbonate. So we need to find lead or carbonates. It's usually the anions. A lot of the times it's the anions that's shown. So carbonates and phosphates show up in the sparingly soluble. We don't have a Pb2 plus exception. Since lead is a group 14. Yeah, group 14 or 4A. So we would say that this is sparingly soluble, which is basically the same as insoluble. On our green sheet, carbonates show up on the first row of our generally insoluble, the lower half, except those of group 1 and NH4 plus. So sparingly soluble / insoluble, depending on which table you're looking at. And then the last one, we've got ammonium chloride. In the top half of our tables, soluble in water, all group 1A and NH4 plus salts, no exceptions. So ammonium chloride is soluble. Questions about how we read or found any of those? Great. Part of the reason that we're learning how to read these solubility tables is so that we can do stuff with precipitation reactions. So you may know that laundry detergent is good for washing laundry, and dish soap, hand soap, not quite as good. Other types of soap, not quite as good necessarily. Part of the reason for that is laundry detergent, not all, but some, most, all, I don't know. Laundry detergent can contain sodium carbonate that can react with dissolved magnesium and calcium ions that form precipitates from solution. So reactions that form a solid from two aqueous solutions. So if you form a solid, that solid is called the precipitate. The key part of this being that we've got two aqueous solutions. We had things that were dissolved and are no longer dissolved. There's a word that describes the category of weather phenomena that includes rain, snow, sleet, and hail. Does anyone know what that word is that would describe all four of those weather events? Something falling from the sky. Precipitation would be the word that I'm looking for. So precipitation, just like water appearing seemingly out of nowhere, out of the sky, or snow or hail or sleet or whatever other things. Something appearing out of nowhere, same sort of idea. Sometimes in precipitation reactions you do get like a snowing sort of look, sort of effect, which is fun. So just trying to make a connection in our brains. An example of a precipitation reaction, if potassium iodide is mixed with lead 2 nitrate, then we get this really bright yellow lead 2 iodide that forms. Which is cool. Some precipitation reactions look neat. We made copper oxide in our copper chemistry lab. That was the black sand stuff. That might have been a precipitation reaction. However, precipitation reactions don't always occur when mixing two aqueous solutions, so here we've got an example of somebody just mixing two things together. You can also just mix stuff together. It doesn't mean that there's always going to be a precipitation reaction that occurs. So how can we know that a precipitation reaction is going to occur? If it occurs sometimes, but not all the time. That's what we want to know. And the way that we can predict precipitation reactions is if we know that only insoluble compounds form precipitates. It might feel a little bit redundant to say that precipitates are only formed by insoluble compounds. It feels a little circular maybe, since precipitates are insoluble compounds. But when we're mixing together two aqueous solutions, we've got dissolved ions, we're mixing them all together, and some insoluble compounds might form. And that's what's going to cause a precipitation reaction. So for example, let's say that we've got Ki and PbNO3 solutions that are mixed. So before we mix them, we've got our two solutions. We've got our potassium iodide. They're dissolved. There's no intact units. We also have our PbNO3 in this other flask. So we've got dissolved solutions, no formula units intact. Immediately after mixing, this is what our flask looks like. So before anything has been allowed to react, assuming we just instantaneously mix them, this is what it would look like. What possible combinations of ions can we come up with? Who can give me one pair that we can make with these ions? Just name two ions that can go together. Those are our four ions. What's one combination of two ions? If you pick randomly, you've got like a 50% chance of being correct. Huh? Potassium and iodide? Yeah, we can mix K plus and I minus. That's one possible combination. What's another pair that we can make? So that's one pair. What's another option? Why did you pick K and I? Because of their charges. What about their charges? They balance out because one's positive and one's negative. So the possible combinations are pairs of positive and negative charges. The actual amount of positive or negative doesn't really matter because we can always crisscross to figure out how they combine. So K and I would be Ki. We could also have the potassium paired with the nitrate. We could also have the lead paired with the iodide. And we could also have the lead paired with the nitrate. Right, those are our 4 possible combinations. That's every single combination of ions that we can make. 2 of those don't make sense to think about in terms of precipitation. Let's see if that's on the next slide. That's not on the next slide. Let's go back. So the solutions that we started with were Ki and PbNO3 If we're trying to predict a precipitation reaction occurring, and we started with solutions of potassium iodide and lead 2 nitrate, do we need to check if these are soluble? What do we have here? What sort of things do we have here in the flasks? What are we showing? Solutions. We've got solutions already of these. The AQ after them lets us know that they are soluble. So that little AQ means that these are soluble. And so if we write those up as our pairs of ions, they are possible pairs of ions. We don't need to check them because we already know they're soluble. We already had them dissolved in solution. So Ki and PbNO3 we don't need to check. This might make a little bit more sense in a couple slides. Okay, so when we mix everything together, it turns out PbI2 precipitates and the potassium and the nitrate remain in solution because potassium and nitrate are pretty much always soluble or are always soluble. So we just get the PbI2. It's there. So if we want to write equations for precipitation reactions generally are double displacement reactions. We've looked at those before. We've seen them before. So we want to write the formulas of the 2 compounds being mixed as reactants. So that would have been the PbNO3 and Ki as our reactants. And then we would split those into ions. Pb2 plus, NO3 minus, K plus, I minus. We can then swap the anions and rewrite them so that we're only checking the ones that we didn't have before. This is to make sure we're not looking at the same compounds from earlier. K with NO3 minus. And then we could rewrite those in their pairs to show what our products might be. So PbI2 plus KNO3. This isn't balanced. It doesn't really matter for now. And then what we would do is see if either of these is insoluble. If one of these is insoluble, we know that lead 2 iodide is insoluble. Then it would get an S after it, and we have a precipitation reaction. If neither of them is soluble, or if neither of them is insoluble, neither of them has the little S behind it, there's no reaction. We've just mixed 2 solutions together, nothing happened. So if both pairs are soluble, write or choose no reaction. If there's a precipitate, if there's an insoluble compound, then it gets the S after it. And the last thing that we would do is balance the equation. You could balance it first, but then if you find out that there's no reaction, then you've just wasted your time balancing it. And great, you did some practice, but on an exam you might actually want that time. So let's predict, as an example, what will happen if aqueous solutions of rubidium hydroxide and cobalt 2 chloride are mixed. Rubidium hydroxide is RbOH. Cobalt 2 chloride is CoCl2. We are told that they are aqueous solutions, and so we can put AQ after them. So our first step is that we want to write out our reactants. So RbOH plus CoCl2, and these might react. If they were to react, they would flip the anions. Those would be the new pairs that we could make. So we can separate these into Rb plus, OH minus, CO2 plus, Cl minus, swap the anions and rewrite them. Rb plus paired with Cl minus, it's the one we swapped. This is the new pairing. And CO2 plus paired with OH minus. And we can recombine these with some crisscross action. So we've got RbCl plus COOH2. Those would be our possible options. This doesn't mean that a reaction has occurred. This is just what we need to check. So check these on the solubility table. So we're looking for RbCl and COOH2. If we look at our green sheet solubility table, in the top section, it says group 1 for generally soluble, and there are no exceptions except for some lithium pairings. We have a group 1 metal in rubidium. Since there's no exception listed for rubidium, RbCl is soluble. So we would give it the AQ. And then we need to look at COOH2. Cobalt is not on here, but if we look at the very bottom of our green sheet solubility table in the generally insoluble section, we see OH minus. So hydroxide is there, except when paired with group 1 or ammonium. We don't have group 1 or ammonium. And it's slightly soluble with calcium, strontium, and barium. Do we have any of those? No, we don't. And so that means that this is insoluble. So this gets an S behind it, so we do have a reaction. The last thing that we do is balance the chemical equation. So that's going to end up with us putting 2's in front of both of our rubidium compounds, and then it would be balanced. We did balancing a while ago. I can show you again if you want but not today, not right now. Questions about any of that? All right, I'm going to steal a little bit of time from our lab to finish out the chapter. I'm skipping over a couple of other examples of how to do those double displacement reactions. There are multiple types of equations. We have what we've primarily been looking at, what we've almost exclusively been looking at, which is a molecular equation. Our molecular equation shows complete neutral formulas, just like molecules are neutral. So we're showing no charges. We could also call this a complete chemical equation. This is what we've been looking at. We've exclusively seen molecular equations, complete chemical equations. There's another type of equation called a complete ionic equations. For complete ionic equations, we show ions as they are. So some of them will be in solution. So we can separate things with AQ after them. So if it's got an AQ after it, that means that it's aqueous. That means that it's dissolved in solution. And we talked about how when things are dissolved in solution, the positively charged, the negatively charged ions separate out. That's how they actually exist in solution. So a complete ionic equation shows us what it actually looks like in solution, the actual state of all of the chemicals. If they're solids, liquids, or gases, they're not dissolved, and so they're intact, either because they're a precipitate or insoluble, or they're just a liquid or a gas. So for a complete ionic equation, we're going to separate things that have the AQ after them. There's also a simpler version, and for that we need to explain the concept of spectator ions. What do the spectators do at a sporting match? They watch. Do they play the game? No, they just sit there and look, right? Spectators are not integral to the game. They don't actually participate in the game. There's like a little bit of plus or minus on that because they do influence, like, you know, the energy in the arena or whatever. But for the most part, spectators just watch, they don't participate. And so spectator ions are things that are unchanged on both sides of the equation. That's how it applies to ions. Spectator ions don't participate. And so we can remove spectator ions from our ionic equation, our complete ionic equation, to get a net ionic equation. So this is like after your taxes get taken out, you get your net pay. Net ionic equation, we're removing all of the extra stuff. So we've removed the spectator ions to get to our net ionic equation. So this shows only the species, only the different types of molecules and ions that actually participate in the reaction. So a summary of these three types of equations. We've got our molecular or complete equation. This is the one that we've been looking at. It's complete and neutral formulas. We've got a complete ionic equation that shows the AQs dissolved. So it shows them separated out into ions. And we've got the net ionic equation that removes the spectator ions. So for our complete ionic equation, we're going to separate the AQs. For our net ionic equation, remove spectators. And we've gotten an example that I'll go through just so we can see it in action. So consider this reaction occurring in aqueous solution. Write a complete ionic equation and a net ionic equation for the reaction. So we've got our complete molecular or complete chemical equation. For our complete ionic, we want to separate the AQs. So that's the barium chloride, the sodium sulfate, and the sodium chloride. So barium chloride separates to Ba2 plus 2Cl minus. We've got a subscript of 2 on the Cl, and so we put a coefficient of 2 in front of the Cl minus. And then from our Na2SO4, we've got 2 sodiums, each with a 1 plus charge. We've got 1 sulfate with a 2 minus charge. You might see these often represented with AQs behind every single one of them. I don't want to write it out. So those are 2 things that have AQ in front, behind them. BaSO4 on our product side has an S behind it, and so we're just going to write it in the way that it is, just BaSO4. And I'm going to write an S behind that because it's solid. And then our NaCl, we distribute the 2, so we've got 2 Na plus 2 Cl minus. Any questions about how we got to our complete ionic equation? So just separating out all of those things. And now we want to do our net ionic equation. For the net ionic equation, we're removing spectator ions. So removing the things that didn't actually do a reaction. There's a couple of ways we can identify things that didn't participate in a reaction. We can either identify the things that participated in the reaction and only write those things, or we can try to look at what's the same on the right side and the left side in our net ionic equation. What didn't change from the left to the right? Give me one thing. Do we have BaSO4 on the left side? No. We don't, right? We have BaSO4 on the right side, but not on the left side, so that's not it. Thank you for guessing. What's something else? Something that is the same on the left side as it is on the right side. Sodium. So we've got Na plus on the left side, we've got Na plus on the right side. So that's one thing that didn't change. It's exactly the same on the left and the right. What's the other thing? Yeah, it's the chlorine, the Cl minus. So we're going to remove those. We're going to rewrite everything except for those. So it's Ba2 plus SO4 2 minus. We removed the Cl and the Na from the left side. And these go to BaSO4 solid, and we leave off the Na and the Cl on the right side. So in this top line, this is our complete ionic equation. This bottom line is our net ionic equation. Questions about any of that? Great. Then that will do it for whatever chapter this is.